Hello, we're going to talk today about line integrals. Over vector fields. So what we mean by this is we have some plane here. We could do this in 3 dimensions. It would just be harder to draw. And we're going to have there'll be a vector field on it, and then we're also going to put a path like so. So we're going to have a curve here, C, and it's defined as r of t, the vector of all the points in the xy plane, r of t, from t equals a to t equals b. Okay, so down here we'll have t equals a, for instance, and up there t is equal to b. And the vector function, we can define r of t as the vector function x of t and y of t. Likewise, f of x comma y is a vector field, and it's not defined. It's not just creating a single line in the plane. It's a vector field. So we like to we'll just draw an example vector field. So I'm just drawing some arrows that are filling the plane. Some function, a vector function, defining a whole field of vectors in the plane like that. So what we want to do is talk about what happens when if f works or represents a force field. So some examples would be wind resistance, so if we're if we're at a point sitting in this plane and there's a velocity field of wind flowing across this plane, and every time we go forward in the plane we have to move against some wind resistance that's given by this vector. So there would be some wind going that way, and if we're headed this way we're going to have to walk into the wind, and that's going to produce some sort of force, and we have to overcome that. So that'd be a air resistance field. We could also have electric fields. So in this case, what would be interesting then would be if we have some charge and we want to move this charge along a path going through this electric field. We want to know the work that's done against that force. In this case, it's an electrostatic force. And then there's also gravitation. In gravitation, then, we're talking about a mass. There'd be a mass that we're moving through a gravitational field, and that would produce the gravitational field would be the force on that mass as we push it through the field. Okay, and so those are some examples of the kind of thing we want to do. So what exactly do you want to compute here? What we want to do is talk about the work. So work is an energy, and it's defined as the force times the distance. Alright, so in the most simple terms, it's just force times distance. We have some force we're working against, and we push something against that force, or we move through that force. It takes a certain amount of energy, and we call that energy work. And so that's certainly true for all of these cases. If we're if some object is trying to move itself through a wind resistance, we have to actually expend energy to do so. If we want to move a charge, an electric charge, through an electric field, that as well takes energy, and also moving a mass through a gravitational field also takes energy. So force over distance, and clearly if we're going to push some mass or some charge or some object through on a path like this, which we're going to call C, And there's a force field defined at every point, so we can think of this as every point along this path defines we can define a force on that's located on the path. So as we move our particle of some type through that field, the force it might experience, it might change direction slightly as we're moving along that path, and so we have to find a way to compute the energy as that force over the distance, where the distance now is a curved path, and the force might not be constant. So both of these may not are going to be there'll be a curvy path. So the distance itself will be a curved shape of some type, defined by c, and the force may not be constant over that space. So so how do we calculate it for this more general case? So again, in the most simple case, it's force times distance. But in general, right? So we can go back to our vector version. So the vector work, it's going to be the force, and now it's going to be a vector with a dot product over some distance d. All right. So generally speaking, what we have is some vector represents the force, and at some point, and then we want to move, if we're experiencing the same force over some distance d, we want to go from that point to this point, and there will be some force that we have to move against. And with these two vectors, then the work done is equal to F dot d. Okay, so recall again what the dot product is. So if F is equal to the vector F1, F2, being the two entries for x and y, and d, the vector, is equal to d1, d2, then the dot product F dot d is equal to F1 d1 plus F2 d2. Okay, so that's what the dot product is. And another nice thing, a consequence of the dot product is that it's always going to be equal to the magnitude of the force times the magnitude of the distance times cosine theta, where theta is the angle between the two vectors. Okay, so there's our basic definitions of vector work. Now, clearly, as we're moving our particle through this vector field, what's going to happen is we're going to have the force will change, and the distances that we're pushing will change. So let's get ourselves a new sheet of paper here. I'm going to draw again our picture. So again, that's x, and that's y, and we have some curve, and so I'm going to break it up like this. So what we're going to do is we're going to break our path into small pieces. That's what we always do in calculus when we're talking about integration. And each one will be a di, and over that there'll also be a bunch of, so we'll have in general a force field defined everywhere. So I'll call that di, this vector going that way. But then there's also going to be some force, which I'll call F, Fi. Likewise here, there'll be some Fi, and then the di is going to be the link between the two, and so on and so forth like that. And so the work, the total work, and I'll put that in capitals, will be basically the sum of all the Fi's dot di's, I equals 1 to n. So we'll have to do every single one like that. Right. Now, obviously, what we always do in calculus is if these represent tiny little path lengths, we take delta s going to 0, and then the work then becomes some integral over c we got to figure out how to represent that times a ds. Okay, so what do we do? What's in there exactly? So we know this, but we got to figure out a little bit more about what f is and what d is, and how to represent it in terms of tiny lengths of the path. Okay. All right. So let's think about that. So like I said, the vector function r of t is equal to x of t, y of t. All right. So from that point here, let's say that that's at t, and here that's going to be t plus delta t, right? So the link between the two will be our vector we'll call d, right there. So d is going to be the vector r of t plus delta t minus r of t. Now, we've done this many times before, and we know that we can always approximate that as the vector r prime of t times delta t. Okay, so that's one way we can represent this. So that represents our vector. So one way we can write down this and then say that over this short period of the short little piece of the path, we have some vector f that represents the force we're working against then, and then the work is going to be then a to b, integral from a to b, f, and now we're going to define it at x of t, y of t, and we're going to dot it with, this is the vector function, r prime of t dt. So that's one way of representing our work integral. All right? So let's break this down a little bit further. Another way to think of it is that we have, again, this vector function f, and it's defined on the curve is to be this particular vector here. We have some length vector here, a length, d, and we have this delta s length. So another way to write this vector, d, is to write it as the unit tangent vector times delta s. So what do I mean by the unit tangent vector? It's the vector that it's in the direction of the velocity, but what we're going to do is divide by the length of that vector, the velocity vector, as a way to take away the length. Okay, so this way this has a unit length to the vector, and so this dot is not a dot product, that's just a multiplication because this is a scalar value here. So that sets the length of the thing. So another way to write this, the more abstract definition, is we write it as the integral over the path of f dotted with the tangent vector. And again, the tangent vector is always this vector t that's pointing in the tangent of the, that's tangent to the curve. And we're taking the integral over c ds. All right. So why is this true? Recall from the previous video that ds is equal to square root of x prime squared plus y prime squared dt. And we know that r prime of t is equal to the vector function x prime, y prime, and the norm, or the length of r prime, of course, is square root x prime squared plus y prime squared. And so we see right here that that is dt, which is how we can get between these two. So ds then we can replace with this here, and remember that means that t, recall then, is r prime, the vector, and so these will cancel and you get back to this result right here. So again, this is the abstract definition. This is how we express it, the integral in a general form. And this representation here is the more constructive form. This is the form that tells you exactly how to compute it for a particular path that you parameterize by time, going from t equals a all the way to t equals b. Okay. So again, this is how we write it to represent what we want to do, and this is what we write when we actually want to do it. Okay. So let's give an example of a vector field. Okay, so I'm going to give a simple example. F, and we're going to define this in polar coordinates. Theta r, or r theta. We're going to define it as negative sine theta over r squared. We're going to put the unit vector I going in the x direction plus cosine theta r squared. We'll put the j vector. So let's write down what this looks like. What does the vector field look like here? All right, so let's try a few points here. Let's try r equals 1, just to keep it simple, and theta equals 0. Okay, so when theta equals 0, sine is 0, so there is no component of the vector at this point here. So that's r, so we'll say that's r of 1, and theta equals 0. So we're at that point there. There's no component of the vector that's in the x direction, but there is a length of 1 in the y direction. So just going up, it's positive. All right. Now we can try another point. Let's try r equals 1 again, and r is equal to pi over 2. And we plug that in. This becomes negative 1, and that becomes 0. And so here we have another vector, and it's pointing that way. And if you keep going, of course, you find there's another one that way, and another one that way, like that. So there's sort of a circulation going on in this thing, and you can keep doing looks like that. Like that. All right, so what about when we take r away from 1, right? What if we make r equal 2? Well, r squared becomes 4, and obviously that's a smaller vector, so when we go out to 2, we get a much smaller vector. So they'll still be doing this thing, but they'll just be shorter. Likewise, when we go inside, if we go a little closer to the origin, now at the origin, of course, r equals 0, we have a division by 0, so that's a problem. But as we get closer and closer to the origin, the vectors need to be getting bigger, right? The force field is stronger there. And so on and so forth. So we get the idea. They get smaller as you get out here. And they get tiny. So now I'm going to talk about, so we've defined our vector field, but we need to find the path we want to integrate this on. So how about the path? The path C is going to be the function r of t is equal to, we'll say it's cosine t times the x unit vector plus sine t times j. So this is and we're going to take it from t is equal to 0 to pi. So this is a half circle. All right, so we're starting here, and as t goes through, we're starting here. We start at when t is equal to 0, cosine is equal to 1, and sine is equal to 0. So we're starting right there at this point, and we're going to be taking the path through this half circle. Okay, and that's going to be our ending point. So there's our A and there's our B. All right, so now what we need to do is compute. So remember the formula. The formula is the work is equal to a to b f at the parameterized dotted by r prime of t dt. So what is f of t? So we know f for all thetas and all r's, but we need to find what is f actually on the path itself, because that's all we really care about for the vector field. Once we pick a path, the vector field, what happens out here is irrelevant. We need to just find out what the vector is, what the vector field is indicating on the path itself. That's all we need. All right, so we have to identify. So r in this case, r is just going to be 1. R being the scalar value, not the vector value. And theta is going to just be equal to t. All right, so that means, so f of t is going to be negative sine t times I plus cosine t times the j vector. Okay, so what then is f dot r prime? Well, we just need to calculate r prime now. R prime is going to be, well, here's r up here. That's going to become negative sine t I plus, sorry, plus cosine t, the j vector. Okay, so good. So now f dot r then will be if we multiply them together, we have to multiply the x components. Negative sine times negative sine becomes a positive sine squared t plus cosine times cosine is going to be cosine squared t. All right, so I said this is a simple example. Sine squared plus cosine squared, of course, is 1. So our integral then becomes work over the path f dot t ds becomes integral from 0 to pi of 1 dt, and when we compute that, it will just be pi. So we see that the direction we're heading, going this way through the circle, and the vector itself, the f vector in the vector field, are both going in roughly the same direction. They're actually going exactly the same direction. F happens to be tangent to r prime, so they're collinear vectors, and so the dot product's always a constant. But this is a simple example. But the idea is that this is a positive work, so it's greater than 0, and one way to think of that is that we're getting a push through this on this path going through the vector field. So obviously, if the vector field was pointing the opposite direction, like that, then this would be a negative value. So negative work, you can interpret that as being work that we have to put into the system. But the sign, of course, we can always change our sign convention to fit the problem. So hopefully that gives you a simple example of what line integrals are in vector fields. Thank you.